Record. All right, on the right-hand side of the course page, so the wind and wave correlation thing, I gave you that like on Monday. If you didn't finish that yet, you finish that for today, and then you hopefully picked up a thing on your way in that says waves and tsunami. If you're remote, in the folder for for waves, tides, and coasts, that's chapter 8, 9, and 10. There's another thing here that says waves and tsunami. And the waves and tsunami link, you click that, brings up a thing that says waves and tsunami 2020, because it's like the 2020-2021 school year. And I don't know why I'm not logged in. That's weird. All right, so I want to go over some basic stuff about different ways that waves are made, the kind of energy it takes to make the waves, and then the effects that you get from different kinds of wave activity. So, like the ocean isn't perfectly flat and calm all the time. You can get waves that are driven by wind. We also have long-term waves that are generated by the sun and the moon. Those are called tides. And then there are individual events that are one-off events called tsunami. And I want to clear up some misconceptions about tsunami. This whole thing is about like what happens with the physical motion of waves. So, you good? And the reason why we care about waves is not only can it be a hazard to navigation for boats, but wave and tide action near coasts is very important for transporting like sand up and down coasts, in estuaries, in places that are like mangrove forests. You get the tides will come in, the water rises up, the tides will go out. You get this constant washing back and forth and cleaning at coastlines. Wetland areas get inundated with water and then dried out. Those wetland areas near coasts are very critical to sustaining life in the open ocean, and the tidal action and wave action around coral reefs is very critical for the survival of the reefs. So there's an awful lot that you already know that goes into understanding waves, and then waves and tsunami and tides will play a very important role in what we'll talk about for the whole rest of the course and stuff like that. Okay, so the three main waves that waves are generated is by wind, and it turns out that when wind blows across water, it pushes the water along, and you can end up with waves that are relatively small up to very large waves if the wind is really, really, really high. There's a particular thing about wind-driven waves at coasts. So here's a picture of like a resort town. This is down in Florida. So here's the ocean, and you got open water, and then here's land over here. So if the sun is shining on the land and the water evenly during the course of a day, which one heats up more, the land or the water? The land. The water has a very high heat capacity. It's very difficult for water to change its temperature. So as the sun shines down, what we end up with is very like warm air over the land and relatively cool air over the water. If the water temperature is 70, the air over the water is going to be right around 70. But the sun can shine on the land here just even literally just 100 yards inland, and surface temperatures here can, 100, 120 on pavement, get really hot, right? And then at night, cool way back down. Surface of the ocean isn't going to heat up to 100 degrees Fahrenheit in the course of a day and cool back down. That doesn't happen. So this whole plan about convection currents, we first looked at convection currents with the motion of magma within the earth causing continental drift. We get convection currents in the open ocean where you got warm air or warm water and cool water. The warm air is buoyant, it rises up. This cool air is more dense and it like falls down. So if you have air that rises up here and air that falls down there, this air has to go somewhere as it falls. This air has to go somewhere as it goes up. So it turns out that what you end up with is this convection current of air. And on a sunny day near a coast, this wind constantly blows kind of in this direction. And that's called an onshore breeze. If you go to the beach and you're standing here on the beach and it's a sunny day and you're facing the ocean, guarantee you the wind's going to be blowing toward your face as this breeze continues along. And then at night, the sun goes down, the land cools down, the breeze slows down, and the waves get smaller. But what's always true, if you're ever at the ocean, is the waves always come toward the sand. Like you'll never see the waves like going out. That almost doesn't make any sense, you know? The waves come onto the shore. They are constantly blown from the open ocean onto the sand. And why that happens is because of this convection current in the air. Warm air rising up, going out over the ocean, cooling and falling down and being blown in. So the greater the, it turns out on, if it's a cool day, the sun's not out, these waves are real low. You want real big waves? Nice, clear, sunny days where you get excessive heating on land causes this wind to get even stronger. And this onshore breeze will drive waves in. Now, when you're also on the beach and you're looking out into the water, you know that the waves are like really big here close to the shoreline. They're a little bit smaller further out. And if you look way out, they're like really small. You don't see them so much. It's almost like they come out of nowhere and they rise up. So there's this phenomena called shoaling. And section 8.4 in your textbook has a pretty good description, but this thing that I just gave you has kind of like a little ramp kind of deal. So how it goes is if the ocean floor is like this, and then you have the beach, and the water level is like that, as this wind is blowing toward land, it pushes this water forward. So imagine you've got like a column of water here, and it's shoved forward. This column of water is relatively high. It's a tall column of water, and there's a disturbance here where there's a crest and a little trough. But as that like disturbance moves toward land, the depth of the water decreases, and that causes two things to happen. It causes the water to slow down, and also this energy has to go somewhere. And it turns out that if this is the length of the whole wave with a crest and a trough, that wave gets a lot shorter and it gets much higher. So what happens is as the wave approaches shore, we get this phenomena called shoaling. And the shoaling phenomena, shoaling is a term that's used for, well, fish can shoal. That's like when groups of fish are swimming together. But fish that come up near shore are also called shoaling fish. But the phenomena where the water comes up, that phenomena of shoaling is that the waves get to be a shorter wavelength and they grow in height. So here's another way to see it. If the ocean surface in equilibrium is like that, and then the sand rises up like this, out here you get relatively long wavelength. The waves are really long and not very high. But the closer you get into shore, the higher the waves become and the shorter they get. And then finally, they're really tall like this. But the deal is, because I said that the waves slow down, out here they are moving really fast. Here they're slower, and here they're slower yet. This wave energy that's up at the top here, it has inertia. That inertia makes that water want to travel at a constant speed, but the bottom of the wave gets slowed down. So the other effect that we see isn't just that the wave gets shorter in length and taller, but because the water energy at the top of the wave has some velocity where it's moving fast, it ends up traveling just as fast, but the base of the wave slows down. So the wave doesn't just get to be shorter and taller. Instead, this wave, when it's out here, is like that, but this top energy keeps on going. So the wave ends up getting like, kind of like, I guess you could say, like non-symmetric. This top energy with this high speed keeps going fast, but the base of the wave is slowed down. And then the next wave, you know, it can crash because this top energy, as it's pushed up, but it's still moving fast, and the wave ends up crashing on top of itself. So really, the wave, when it's very far out, it's moving along really quickly, but the base of the wave ends up slowing down, and the top of the wave keeps going quick. So waves always work their way toward the shore. They get shorter in wavelength, and they crash over the top. And even if you've never been to the beach, you've at least seen video of that happening. That's kind of not a surprise. So waves near the shore, that's commonly just like what's going on. Even out in open water, as waves blow, as wind blows across water, you end up getting waves. So, and the length of those waves can vary, but they're not really super long. From, you know, from a couple meters to whatever, and you get a wave every like second or up to 30 seconds. So if you're at the shore, you might get a crashing wave every like 10 seconds or something like that. Not a big deal. The other phenomena that's regular is about tides, and we're going to do separate work with tides. But because the water on the Earth is attracted to both the sun and the moon, that attraction of the water on the Earth to the sun and the moon causes like this bulge of water, which propagates a wave around the Earth, and tides have a period of about 12 hours. But the other phenomena, so that should make sense to you. On page 258, there's a description of a wind scale called the Beaufort scale. The Beaufort scale is a scale that relates wind speed and wave height, much like what you did in the wind and wave correlation activity where you looked at real-time data. But the other phenomena are about tsunami. So the first thing I want to clear up about tsunami is there's this big myth that it's like this is the ocean floor, and then you have like a city here or whatever like that, and the ocean is like this. There's this myth that tsunami are these like giant waves, you know, which are higher than buildings that come in and just crash into buildings. That's not how tsunami work at all. It's not a vertical wall of water that's crazy, crazy tall, where this is like a skyscraper or something like that, or a house. Instead, tsunami have a completely different behavior, and it can actually be even more frightening. And it comes down to how tsunami are created. So the three general ways that tsunami are made is by, hold on, I don't know why that happened. Get back to this. Show desktop. I don't know why I have an eraser on there. That's weird. Are by earthquakes, volcanoes, landslides, and seamount slides. So you can already guess how a tsunami could be generated based upon what we did with seafloor activity. So it goes like this. Here's like the seafloor, and then here's like a shoreline, and then here's like the ocean level. Now, the seafloor itself can have a fault. That fault on the seafloor could be a convergent fault, it could be a divergent fault, it could be a mid-Atlantic ridge or something. And it's when that place where the two plates meet up shifts that it can cause motion of water. Yeah, so there's different things that happen. Here's the thing, when there's a tsunami or when there's an earthquake, there's oftentimes a tsunami warning generated immediately. But it's not clear what kind of earthquake it is, and the type of earthquake plays a big role. So on the ocean floor, if it's a transform fault where one slides past the other, like in this direction, that won't necessarily generate a tsunami. Transform fault where one's going this way, one's going this way. If the ocean floor slips that way and this way, the height of the water doesn't really change. That could be a very, very dramatic tsunami, or a very dramatic earthquake, but no tsunami. What you worry about are the kind of faults where if the ocean floor here lifts up and this part drops down, if the ocean floor lifts up to here and this part of the ocean floor drops down to there, this water up here ain't going to stay level. Instead, this part of the ocean goes up and this part of the ocean goes down. And now you have an ocean surface that's like that. And that's bad for this land, because if the ocean floor rises to the west and it drops to the east, all this water here has got to go somewhere. You know where it goes? It just spills down on top of this. Yeah.
So, you know how in the movies it'll show like the water dragging out before the big wave?
Yeah.
Does that happen?
That can happen. Okay, so this type of event, you know, for every crest, there's a trough. In other words, waves are never like just a bump. Instead, there has to be a trough. So preceding every crest, there's a trough, or after every crest, there's a trough. So I'm going to show you some videos where you're going to like actually see this happen. One warning that a tsunami is taking place is like, you're here on the beach and you may be a local and you know where the beach is, you know where the water meets the land all the time. You're like, that's where the shore is. You feel this earthquake, and then all of a sudden the ocean drops down, it goes away, the water rushes out. That's not something to hang around and watch, because if the ocean drops 10 feet, guess what? There's a wave coming in that's 10 feet higher. And if 10 feet is like up here, well, you're in the way of some water coming at you. And a thing to know is 1 cubic meter of water, that's a box of water that's 3 feet by 3 feet by 3 feet. About the end of my desk here, like the volume of the end of the desk, that has a mass of 1,000 kilograms, which is 2,200 pounds. A box of water that's a cubic yard weighs 2,200 pounds. And if this water is coming in doing 50 miles an hour, every box of water that's a cubic meter is a ton. So you're getting hit by like an enormous amount of water moving very, very, very fast, and it can cause complete damage, utter damage. So this is one type of thing that can happen. Another type of thing that can happen is kind of the opposite. So what if the ocean floor does this kind of thing, where this side drops down and this side lifts up? Well, you're going to have a lifting of water here and a drop of water on this side. This water is going to go that way, and that can cause the water to rush out. Except when water goes out, it's going to hit and come back. You know, it sloshes around, and depending upon the topography, you can end up getting a big problem. So earthquakes can cause tsunami. Another thing that can cause tsunami are I don't know where this one go. Go gadget go. Are seamount slides. So on the ocean floor, you can have like a seamount. And just like on land, how we can have landslides, these seamounts can also be unstable. And if you have a seamount slide where this, top of the mountain falls down, as that top of the mountain falls down, it can also push a wave. And that wave that gets pushed, then travels toward land. And an important thing to know is in open water, the speed of a tsunami wave is usually on the order of 600 miles per hour. About the speed of an airliner. You're close to the speed of sound. A tsunami can make it all the way across the Atlantic Ocean in about 5 hours. There are no ships that can do that. In fact, you would have to be in a very high-speed jetliner to keep up with and race a tsunami. So you've got lots of water going really fast, but as it approaches shore, that wave has to slow down. It's going to slow down to the same speed as any other wave. But as a result of it slowing down, it's going to really build up to be quite large, but not like a vertical wall of water. The other thing that can happen are landslides. So how that goes is you could have, this particularly happens in bays where you have, I'll draw it like this. Here's like the ocean level, and you have maybe a mountain over here, and this mountain could fall into the ocean. And as this mountain falls in and all the soil goes down in, it'll push the water and generate a wave, which then cause inundation over here. And in fact, the largest tsunami that's ever been confirmed is as a result of a landslide, and it happened here in the United States in a bay up in Alaska called Lituya Bay. And I'll show you how high that tsunami wave got on the other side, because there could be like another mountain over here, and as this water rushes down, this wave can then rush up the other side of the mountain and be like really phenomenal in its damage. Okay, let's see. So earthquakes, volcanoes, landslides, seamount slides, and that's the common thing that takes place. Okay, so in the waves and tsunami activity itself, on the thing about tsunami here, so what about horizontal or vertical motion on seafloor? Which is more common to cause a tsunami? Besides faults, what other kind of events cause tsunami? What's the typical wavelength? So on really in section 8.5 of the textbook, there's good information about tsunami. And then there have actually been a few really remarkable tsunami that have happened in the last 10 years that are, I guess you could say, totally unprecedented. There was a massive tsunami that took place in Indonesia. I guess it was like 2006 now, 15 years ago. The tsunami that happened in Japan in 2011. There was a really remarkable tsunami that took place in Greenland that I'll show you a video about. And part of the thing about tsunami now is people have, like, everybody's carrying cell phones with them with video cameras. People have surveillance cameras. So there's far more video available than back in the day. If a tsunami took place in the year 1850, it could be recorded as having happened. There's no physical evidence of it anymore, and nobody had video of it. So we've learned more about tsunami recently, and unfortunately, there have been some completely devastating tsunami in the recent past. All right, so in the course, I have, in the plan for the week, I have a bunch of links, and you can watch wave videos and tsunami videos all day long on the internet, on YouTube. But here in the plan for the week, so there's this one here that's a general animation of tsunami activity. Because whenever I draw it as a physical drawing, it only means so much. All right, so this shows kind of like the physical motion and stuff. And there's all right, so here's one, a volcanic eruption. There's a seamount, or the mountain falls into the ocean and it generates a wave which goes out. That wave travels very, very fast here, like up to 940 kilometers per hour, 960 kilometers per hour, which is 600 miles per hour. But in deep water, the wavelength isn't very high. So in fact, if you're out in the open ocean on a ship, a tsunami could travel past you, and the wave height is half a meter, which is like foot and a half. It's no big deal. You might not even be able to detect it. But as that very fast wave gets toward shore, it's going to slow down. The wave height's going to increase, and that very short wave ends up to be a very, very, very tall wave. The wavelength decreases, and you get huge amounts of inundation. So in the videos you'll see about the wave action for tsunami, it's more of an inundative wave. So here it might only be a few feet high, but if the land is only a few feet high, that wave can travel inland, enormous distances, sometimes many, many, many miles. And because it's still traveling at a high speed, you can just be sitting on a park bench, and then this water hits you and you get slammed up against a tree, or the buildings fall down. Buildings are relatively buoyant. If you build a house, a wood frame house, wood floats. So whether it's freshwater or saltwater, the whole house can just get picked up and then get tumbled around and get damaged. So the real risk with tsunami is not so much that there's this giant wall of water, but this incredible amount of flooding. Also, when the flood goes in, it's going to have to recede and go back out. So there's a risk of not only property damage and injury as the wave comes in, but you get backed out in the ocean, and everything goes back out in the ocean. So now you could be injured or hurt, or your property is now, spread out in the ocean. And it's not as if there's a single wave, but a number of waves. And it's not necessarily that the first one's the big one. It could be like later waves are actually bigger. So that's the general idea. Okay, then let's see. So it was 2004. There was a major earthquake in Indonesia. They call it the Indonesian earthquake, or the Banda Aceh earthquake. It's one of the largest earthquakes that ever took place. Oh, well, that's a bummer. And it happened right around Christmas time. I think it was like the day after Christmas.
I think I remember seeing this.
Yeah. So this isn't. We'll find a video of inundation, but this is a video showing the earthquake location and the propagation. So here's where it is. This is Indonesia. Well, Indonesia is all this group of islands around in here. The earthquake took place right here, and that earthquake caused a tsunami. The earthquake location was very close to shore. It was only minutes warning. It was like earthquake takes place, and 5 minutes later, everything is total chaos and disaster. But this shows here, up here is the ticker. So 0 hours, 3 minutes after the earthquake takes place, you can see how far the wave has already traveled. This clock will keep running, and you can see that the wave will propagate all the way across the Indian Ocean, hit Eastern Africa, Madagascar, but also bounce back. It'll reflect off the shores and travel around. So the earthquake took place all along one giant fault. It was a very massive earthquake. This is in slow motion, but then they're going to pick it up. So this is 1 hour, 2 hours, 3 hours, 4 hours. So within within 4 hours it hits Australia, and then 7-8 hours in, you're on the west coast of Africa. This is actually a relatively shallow water, but these waves continue to bounce around all up in here. So it caused enormous amounts of damage and an awful lot of loss of life. Well, I just got to find another video because the other one went down. Indonesia tsunami. Let's see. I don't know what just happened. Yeah, there's a whole bunch of them from different perspectives. But this is shortly after the tsunami takes place, or shortly after the earthquake takes place. And you can see here there's this bay, and there's a huge amount of disturbance in the water and with the boats. You can see some boats have actually like dropped down and are sitting on the bottom because the water has washed out in that location just briefly. And then here comes the wave back in. These people need to get out of there, including the person holding the camera. It gets kind of chaotic. But let's see. There's a one that's really good that's from the resort. So yeah, you can see the crest of the wave out there coming in. And then this, beachside road and all these buildings here end up getting enormous amount of damage. So cars are still driving down the road. People are still like doing their thing. So you see people climbing stairs or like getting up. Anyway, so that was a pretty massive event. The better one that's more well documented is the tsunami that took place in Japan in 2011. This caused an awful lot of damage, but most importantly, the Japan tsunami damaged the Fukushima nuclear power plant, caused a total meltdown of a few reactors, and it's the worst nuclear disaster ever. So this is a good example of the water washing out. This is a bay, and you see this is land here. The water has washed out. These boats are sitting on their keels, and there's no water. So the earthquake has taken place, and people are like, yo, the water washed out. But a tsunami warning has been issued. Notice how these boats are sitting really low relative to the pier. That's not typical of where they should be. And then here comes some of the first wave. And you see, like, it's not super fast, but it's coming up. The water level's rising. This is really mud here. So there's really no water here. So you got this muddy kind of water rushing in. So notice the height of this seawall, and there's a seawall right here as well. And I'll go forward in time. And the water is really coming in, and the boats are rising up. But this water will crest over the seawall. There's people still driving down the road. Yeah, it could be a barge that's overturned, or you're going to see a lot of stuff moving here real soon.
Why didn't they respond to it immediately?
Well, people did, and it turns out like some people are still driving. They may be trying to get to where they need to go. The person videoing this, they're up on a roof along with other people. There are buildings that are good to go for tsunami. They're designed to be inundated in the first couple floors. You know, walls aren't very substantial. The water rushes in and rushes back out. But let's see. I gotta get to the overtopping. All right, so now here's where the water starts to overtop that seawall and then come in. The boats are being ripped from their moorings, and now it's bad. You see the buildings start to get lifted off their foundation. Cars are buoyant. The cars will all float. And you're not even going to see that seawall in a moment. Like, the water will be higher than the seawall, both in and out of the town.
Just a mess.
Yeah, it's all done, right? I mean, what do you got left?
Wait, so why didn't they respond?
Well, there really aren't people down in here. You know what I mean? Like, you're not seeing death here. Like the person making this film, they're up on roofs of buildings with other people. People run up the hills. You know, you get up out of the way. But you can tell that's bad, right? That's it. So it's not a wall, right? It's not like a crashing bam, but this is almost like as bad, but in slow motion. Yeah, so now you got to figure out how to get that boat on the other side again. And it continues. It just keeps coming, and it keeps going higher and higher and higher. This doesn't get better; it gets worse. You can see it's still coming in. It's still rushing just as fast as it was. So, and it's still running in. You know, we're 11 minutes in. So you've got 11 minutes continuous of water just keep on coming in and keep rising, and it's not good. So that's not atypical of the kind of thing that takes place. Here's the animation of the motion of the surface water. Yeah. So a 9 magnitude earthquake is among the most powerful earthquakes ever to take place. And it turns out, so kind of about this. This is the Pacific plate, and then this is the Asian plate. And the place where the Pacific plate underrides the Asian plate is very close to the west coast or east coast of Japan. So this is the east coast of Japan. That fault is not far offshore. So the places where the earthquakes most commonly take place are around that ring of fire. And so you'll see the earthquake get set off right here, and the time from the earthquake to shore is very, very short. So the time for the tsunami is just a few minutes. But that wave continues across the ocean, and it caused changes in water level in Hawaii and on the west coast of the United States. So here goes that wave, and here's Hawaii. So we can pause it. The distance, so like right here, the water has just gotten to the island of Oahu, which is where Honolulu is, and it's 7 hours, 30 minutes. The water's almost to Seattle. But if we keep running, we'll stop it like right here. That's San Francisco. So you got a time of 9 hours, 43 minutes to San Francisco. And the wave continues to propagate all the way across the ocean. And of course, the wave height is going to be a whole lot less when you're, into Central America and South America, but still have a measurable change in height. So if you were, here on the west coast of South America, like if you're here and you're in a marina, the water may come up like 3 inches and go back down 3 inches. The boat will come up and down a little bit. Not a whole lot. But that's pretty common. The other Okay, the other really, really impressive tsunami is from a landslide. So there was a tsunami that took place in Alaska in a location called Lituya Bay. I'm going to play this on this screen so it's got sound and stuff. If you're remote, in the plan for the week, April 28th, in right beside landslide, it says Lituya Bay tsunami and simulation. Skip ad.
It's one of my favorite places in the world. It's a magnificent landscape. There are mountains roaring up behind it. Glaciers come off those peaks right down to sea level. And you have a bay that is unique along this coast.
Plafka came to Lituya Bay with his colleague Don Miller in 1953. They came to survey for oil.
We didn't find any petroleum in Lituya Bay, but what we did find was something that happened on a cataclysmic scale, and we spent a large part of our time trying to understand it.
What these scientists discovered in the 50s was the evidence for a previously unknown force of destruction. The evidence lay not in the rocks, but in the trees.
One thing that was very peculiar is the fact that mature forests did not extend all the way down to the shoreline, as was true almost everywhere else in this general area. Instead, there were bands of younger trees below mature forest, and the line at which the trees of different ages joined, we call the trim line.
Nothing like this had been recorded before. They suspected the surviving trees from just above the trim line might contain evidence of what had happened many years earlier.
We cut selected trees, took samples from those slices, and sent them to the Juneau Forestry Research Lab and asked them to count the rings and give us an analysis of just what happened to those trees.
This is a photo of a section of a spruce tree that was taken by Don Miller and George Plafka in 1953 in Lituya Bay. The tree was right above the trim line in the bay, and it tells a very interesting story. The early growth in this tree was very good, nice wide rings. All of a sudden, it changes. Something happened to it. Something must have hit it very hard on this side over here. There's a large scar.
The tree ring analysis showed a violent force had struck the entire shoreline of the bay.
So when I talk about the trim line here, all these trees here that are like light green, all these trees are exactly the same age. None of them are any older than any others. And then the trees from here up, they're all good to go. So how do you get rid of all these trees all at once and have new trees grow in? Maybe some loggers went in there and cut them all down, right? But that's not what happened. But how big does a wave have to be? How violent does a wave have to be to take out like a whole forest, right?
The forest looked like it had been hit by a giant wave. For the scientists, it seemed impossible. No wave in history had ever reached anything like this high.
There was some powerful force at work here that created a wave, possibly 150 meters high. That's equivalent to, say, the height of a 50-story building. And we just didn't have any idea of what could do that.
Even the most powerful waves, tidal waves, known to science by their Japanese name, Tsunami, could not have created such destruction. This wave had been caused by something very different.
Well, we didn't know what caused the wave. We considered earthquakes, And earthquakes cause tsunami, but those tsunamis are usually less than 10 to 15 meters. And here we have something that's 10 times as high as that.
So here's an animation of what figure did happen. If you get a landslide that happens within a narrow bay, as that landslide falls down into the water, it causes a huge disturbance in the water itself. So it happened in 1958, which is not that long ago. It isn't like ancient history. It isn't like prehistoric or anything. So this is a simulation of that kind of phenomenon. So what if you have a landslide with a bunch of water that, or a bunch of land that goes into the water?
Red box is accelerated down the ramp at high speeds. The flap opens and the landslide is released to impact the water.
The scientists here made a detailed analysis of what happened at Lituya Bay when 90 million tons of rock hit the water. They wanted to see how this impact had released enough energy to create a giant wave able to reach half a kilometer high.
We adapted our model to mimic a cross-section of Lituya Bay. Up here we have the landslide generator representing the mountain where the rock fell off. At the other end we have a ramp representing the headland where the wave ran up to. And what we found when we ran the experiment was fascinating. What we found explains how a wave could reach the extraordinary height of 520 meters. A high-speed landslide impacted the water. The water moved away so fast that it couldn't flow behind the landslide, creating a large air cavity. This placed far more water than the landslide volume itself, and this explains how a wave can have enough energy to run at half a kilometer and clear out everything in its way.
The speed and size of the Lituya Bay landslide explains how the wave there could be so big when it was generated. This wave did not travel far. It struck land almost immediately. But mega tsunami are also able to cross whole oceans.
So,
Not everybody wants.
and then there's only like a couple minutes left, but oh shoot, it's not there. I gotta find. Why isn't it there? Refresh. I just made the link. Then there was another tsunami created by a landslide in Greenland in 2017. Not this one. But that landslide wasn't particularly big. And it's a vertical video, but at the beginning, the water washes out. So they felt, the person making this film, they literally put it in their window, in their like kitchen, felt some kind of shaking, and it was a landslide from across that bay. First, the water washes out, and now the water's washing in. So you can see this is in Greenland, on the west coast of Greenland, and there's ice and stuff in the water, so it's very, very, very cold. But now the water's coming in, and then the water goes back out. There were actually a series of 6 waves, but here I'll just show you the very end. There's only like a minute left. So there were already 5 waves. This is the 5th wave going out. You can see the water washing down. And then here's the 6th one. So as they wash back and forth, it might not be the first one that's biggest, but here comes the 6th wave coming in. That's that. The person ended up surviving, but it took out like all the homes in that little community.
There's no way to keep it.
Yeah, that couch is done. Couch got damp. Nobody wants a moist couch. That's right. Oh yeah, like when people put couches out, you know, free couch, and then it starts drizzling, and you're like, oh no.
Oh, actually, it'd probably make it cleaner than it already is, let's be honest.
People put the filthiest stuff out on the street too. It'll be like almost black.
One-on-one.
It'll be like, yeah, it'll be dirty.
If you think I don't wonder why half that stuff is
And it smells like dog pee, and
yeah.
it's all stained. One of the legs is broken. That's the kind of stuff we used to love in college, but not when you're like a real human.